Hello and welcome. Today is Thursday, I think. Yeah, it is Thursday. April 23rd. April 23rd. Thanks for tuning in. We ran into some issues earlier in the day, but I think everything is working now and should be stable. If it does crash, let me know in the chat and then I'll see what I can do. But it should be working now. Everything's been running smooth for the last hour or so. We will continue our review series for the AP test. This is review number 4, and if you recall, not yesterday, 2 days ago, we talked about how there's this non-zero y-intercept. You're supposed to answer, the question, and you're supposed to leave your comments below, but no one did. Y'all failed. My AP1 students have been posting comments, so get on their level, I suppose. Get on their level. Yeah. All right. So anyway, some of you started to blur it out. How it's a non-Hookean, realistic springs are non-Hookean, and so initially it requires a tiny bit of it requires lots of force for it requires a lot of here let's use a different color. It requires a lot of force to get a tiny bit of separation, and then afterwards it starts to equilibrate and become Hookean. So it's only Hookean for certain regions. Right. Now when you go beyond this point, it's non-linear once again. No, Ved, you are wrong. So at first there are other intermolecular forces or things that are keeping our spring from stretching, and so it requires a bit of extra stretching to get it to linearly move out, to expand outwards. But our data points that we collected, right, were only for a certain region. It just happened to be a region where it is Hookean. And so by using only data sets where it is Hookean and we do a trend line, the trend line extrapolates data based on a perfect function, right? Based on the fact that we have data that is linear, the trend line will tell you that the entire function is linear. So when you go backwards, you get, a non-zero y-intercept. But in reality, of course, at 0 it's 0. It's just there's this ramp up, and there's no way to get this ramp up without taking more and more data, especially the ones that are much closer towards 0. Okay, so and as you know, if you overstretch it, then a little bit of stretch will give you lots of tension, and so it becomes very non-linear, and then it snaps, and then kablamo, we've turned into, well, it snaps, so there's no force from the spring at all. It just drops to 0. Yeah. What is the upper limit? Upper limit. There's a middle and the median limit where you go off of being Hookean. So there's two words where you go off of being Hookean, and then there's an actual maximum upper limit. You should know these two terms. Chat, what are these two terms? The point at which we break away from being Hookean, and then the point where we essentially break the spring. Oh, we got one, the elastic limit. Yeah, which one is the elastic limit? Here, let's label them. A and B. Yeah. Compression, no, not quite compress. Yeah, it is the breaking point. What do we call that? What limit? So we got A. A is the elastic limit. The break point is called the tensile limit. Yeah. Tensile. That's a good word. All right. Let's move on to today. Today's about energy, our favorite. Yeah, I mean, if there's going to be a mechanics question, there's probably going to be about energy and momentum and stuff. WEPMO. Today is WEPMO day. Easy stuff, yeah. Or dot dx. Remember, it's a dot product, so your vector has to be parallel or anti-parallel. What is anti-parallel? Yeah, parallel and so theta is equal to 180 degrees. Yeah. Which force, actually there are many, but what force is always anti-parallel to displacement? It sounds complex, but it's it's very simple. Like, which force always points in the opposite direction to dx? Yeah, friction does. Yep, we got friction. We got drag force. We have viscous drag forces. If you want to learn about fluid dynamics, consider majoring in physics. Yeah, so good. And recall that a dot product, it gives you a scalar quantity. So if I have a force and using this applied force, we can move it some dx amount. I'll call it delta x. Some delta x amount to the right, and of course we can say that the angle between the applied force and the displacement vector d is theta, so that's why we take fa times x times cosine of theta. Or the other way to look at it is that the horizontal component fax is already equal to fa cosine theta. So if I have a vector that is worth fa cosine theta, and then my displacement vector is x, then the angle between fax, this is fax, the angle between fax and x is how many degrees? Chat, how many degrees of separation do we have between fax and x? Is this a trick question? Yes, it is a trick question. Yes, it is 0 degrees. Good job. So you can see how fax is parallel to delta x, and therefore you get 100% of the dot product, but the dot product is for a portion of the vector to begin with. So it's a roundabout way of getting to the same place. Work is the change in kinetic energy. This is the work energy theorem. Wait, that's ISBO. It is ISBO. Work is the change in kinetic energy. Recall that we have various flavors of energy. All right, give me all the flavors. Here we go. Sour Patch Kids is the sour apples. That's what lightning tastes like. MV squared. Now we have the vanilla flavored Pegmaga. which is mgh, but we know that g is not constant, right? G is based on distance from the center of mass. So we also have ug. Make sure you remember that ug has a negative. Now, technically there's no gravitational gravitational unit on the AP test, but if there were a future test that incorporated all of the physics you've learned, hint, 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 remember that UG is a negative GM m2 over R. You missed the hint there, chalky milk. For AP test or your future potential assessments that you may have. Yeah, AP, it's only, didn't we go over this? It's only up to rotational dynamics, so no shim and no gravitation. We also have, what do we have? PES, which is 1/2 kx squared. Right. T squared prop R squared, no, R cubed, yeah, there we go. Yeah, T cubed. No, it's T squared to R cubed. T squared to R cubed. Yikes, we need to review for those future assessments. But we'll do the extra review after the AP test, right? For the main event. Yeah, of course. How else are you going to get your star? You think it's going to be that easy to be on the wall? That wouldn't be fair to all of your predecessors, and it wouldn't be fair to you, right? So it's for your own good. The virtual wall. Yeah, we're just going to have virtual stars. Any other energies? Yeah, of course we have many other energies, especially with like electrical potential, and we also have rotational K rod. 1/2 I omega squared. All right, this is too simple. This is too ISBL. Let's move on. What is new? I can do that. I mean, I don't have to sneak. I can. I'll do it over the summer after I get my results. I actually have to order new stars anyway. Yes. Here's a new one. Force is equal to negative du dx. The negative slope. Okay. And that's essentially because usually when you do work, you are accelerating the object, right? When you do work, you are accelerating the object, and so when you are accelerating the object, typically your potential will convert into kinetic energy, and so whatever you lose is what you gain via kinetic, and therefore it has to be the negative slope. Wait, why are we saying W? Oh, is it W? No, it can't be W. You're saying energy is equal to the derivative of energy. How does that make sense? Yeah. Just I mean, if you're ever confused, all right, just do the old, just multiply both sides by dx. You get f dx is equal to du, negative du, of course, right? and then you can take the integral of both sides. Please consult your formula sheet. This is actually this is one of those equations that's critical, but is not given in your equation sheet. So this one you gotta memorize. This is why you have that nice 3-ring binder all ready and set up, right? The one that we were talking about earlier, where you put together all of your chapter summaries and your notes all neat and nicely and neatly in a 3-ring binder. Good job, guys. Good job. For the AP test, of course. Yeah. So again, this one is not given on the AP equation sheet. So, and they expect you to have the equation sheet. It's you can't open up a tab or anything like that. I mean, unless you have dual screen. I don't know. If you can, ideally just print it out and have the equation sheet in front of you. That would be ideal. All right. Anyway, stability. When are things stable? So stability was also new. Well, if I have a potential graph, you typically you can set the derivative equal to 0. Set du dx equal to 0. And you can find your minimum to find min. No, it's isn't it when forces? No, it's not technically opposite. It's when you're at equilibrium. This is when net force is 0. This is another way of finding equilibrium. So if you have a system, you're going to be stable, the most stable, of course, when you're at equilibrium. Now, as you can see, I've dipped below the negative. Remember, U is all relative, so you can have negative potential. So it doesn't really matter. It's just all relative to some point. Yeah, when changing potential is 0, correct. This could also be max F though right, for maximum force. What is a maximum force? What do you mean maximum force for a spring? I mean, the spring force equation is linear and it just keeps on growing if it's Hookean. Technically negative, but we'll use absolute value. So I don't know what I don't know. I was thinking like if a spring is oscillating. Oh, interesting. If a spring is oscillating, there's a max kx. Yeah, but this is not. Now follow through what you're trying to get to, right? Yes, it could be oscillating. First of all, oscillations won't be on the AP test, but it could be oscillating. If it is oscillating, when you have maximum force, when you've squished the spring all the way, you're definitely not at equilibrium, right? You're at one of the extreme points, one of the sides. And when you've squished it all the way, yes, you have maximum force, but you have maximum potential energy. You're definitely unstable at this point. Your stability occurs when you have minimum potential energy, and the minimum potential energy occurs here at the equilibrium point in the middle. All right, so what else? So that was work, energy, power. Well, power capital P. Power is work per time. Here's instantaneous power. And funnily enough, the units are watts, which is a joule per second. Is a joule per second. Recall that sometimes we are able to break this apart. Freshmen be like IJ percent, huh? I don't know what that means. Oops, FV. This is interesting in that it assumes a constant force is being applied. And you have a nice constant V. A constant force with a constant V. So a classic example would be where you have let's just make this ideal still, where you have a motor, and this motor is able to do work. What does it do? Well, it's able to, it's like imagine a fishing reel, and it's able to reel in objects. So how much work is this motor doing if we lift this object up at a constant rate of v meters per second? Okay, so as far as the motor is concerned, the tension in the rope is equal to the weight of the object, and we are pulling this up at a steady rate, right? Yeah. So the power that is required must be equal to the force that is applied times how quickly you are doing that work. And in this case, that would be tension, and Ft, because we're going at a constant rate, Ft is equal to m1g. So we get m1g v. No. You definitely need to make sure you mount your motor so it doesn't move. And this same power must also equal the electric power. And how do we find the electric power? IV. This one is velocity, and this one is voltage. Yeah, that's a nice honors physics level question. That's illegal? No, that's not illegal. That's how it works. Yeah. All right. Momentum, lowercase p, is your vector. Anything new with momentum? Not quite. I guess the center of mass was a little different this time around, right? How do we find the velocity of a center of mass of a system? Ooh, chat. Do you guys remember how to find the velocity of the system is the velocity of the center of mass. Close. So treat it like a, to find CM, treat it like a PIC. So M1 V1 plus, now these are vectors, so pay attention to the direction. So V2 is negative, make sure you plug in negative numbers if you are using values, but if otherwise we write it in general form. Is it a lot? No, this isn't. Yeah. So this is the instantaneous velocity of the center of mass of the system as these two objects are moving left and right. Right. So we treat the system as a PIC, like a PIC collision. It's not, it's not the actual velocity after collision that we're trying to find here. We're trying to find the velocity of the center of mass. Yeah, VCM is like there's an imaginary combination of the two things moving. Yep. So this orange box that represents the system is moving at VCM. And if I isolate this VCM, you can see how we get M1 V1. Oh, let me just write it this way. M1 V1 plus M2 V2, and if I had more, I'd just do more, divided by the total mass, M1 plus M2 plus if I had more. Correct? Now one could say that the velocity is just distance over time, right? So we have M1 dx1, M2 dx2 over total. Okay. And so by multiplying everything by dt, we get, or integrating it for a certain amount of time, same amount of time, we essentially get XCM formula. XCM is M1 X1 M2 X2 over M1 plus M2. Okay, and you can do it in both dimensions, or all three dimensions, or any other dimensions you live in. So if you want the y-axis, do it in the y-axis. If you want the x-axis, do it in the x-axis. This is where we start talking about different types of densities. You can have linear mass density, lambda. I'll call it linear mass density. Because we can also have charge, right? So with E&M we can have charge as well. This is kilograms per meter. We can have surface density. lowercase sigma. This is kilograms per meter squared. Then we have rho, which is our volumetric mass density. Regular density. Kilograms per meters cubed. All right. So here's a interesting question. So let's say we have a rod, but the rod has this pointy end. It's now a spear. A pointy spear of some kind. These are some archaic weapons, but it's a cylinder with a very hard pointy cone. Okay, and of course they are made of different materials. If you're fashioning an arrow or something, or a sphere like this, you're probably using like a rock or whatever metal thing, sharp thing you can find. So let's see. Let's say this has some sort of volumetric density rho 1, and this has some sort of volumetric density rho 2. This one is a cylinder of radius little r. No, I'll use capital R. Capital R. Same thing with the cone. And the cone has some sort of height, lowercase h. This has a length, a height of capital H. All right, chat. Find the center of mass for this system. Okay. If you have the answer, please write the answer in the comments below. Yes. All right. So anyway, that's a review session. Now, a couple of you ran into maintenance issues last night, apparently. I hope you learned your lesson this time, in that whatever can go wrong will go wrong. Murphy's Law. This is why you don't wait until the last minute to do anything, because things can go wrong. But I did open up the assignment, so you have until 11:45 p.m. 11:45 p.m. tonight. So there's your extension. For what? All the kids who procrastinated and didn't learn anything in AP Physics 1 ended up running into issues because College Board went into maintenance late, like at 10 o'clock or something like that. So this is like the bailout, that these kids are waiting for. Yay, bailout money! Woo! Big yikes, indeed. All right, so 11:45 p.m. is your extension. A lot of you were close, so that's good. You're close to finishing, so might as well just get it done right now. All right, so get your thing done. Now you should be doing the mechanics stuff. The mechanics stuff is due next week, so do your My AP mechanics homework, and then solve this problem, this pencil spear ancient weapon problem. This is a potential weapon you could make in the new Amazon New World video game. The open world. Uh, yeah, I think it is called New World. It's actually called New World. Uh, so there you go. That's gonna be hard to type. Type what? The Well, do you guys remember how to do XCM? Remember, you set the when you do XCM, you set you set the origin on usually the left side, like this. So you, of course, in an if you were to give an explanation, um, you would state that let the origin be set on the left side of the sphere, and then go on from there. Right? All right. Thanks for tuning in. Leave your answers in the comments below. Do your MyAP homework. I'll see you next time.